So lipids is a broad category of biomolecules, and it's a bit more varied than some of the other groups we've learned about, like carbohydrates, proteins, and for the HL group, nucleic acids. There's not going to be one monomer or polymer for lipids. There's kind of really three different ones that you have to cover. What they have in common is that they are hydrophobic or fat soluble, and they're not water soluble. So they're mostly going to be composed of carbon and hydrogen or hydrocarbon. So they can't form hydrogen bonds with water. The different categories are the fats and the oils, which is really triglycerides. You also need to know about fatty acids structures, which is a component of triglycerides. There's phospholipids, which are very close in structure to triglycerides. And then there are the steroids, which includes cholesterol, a number of hormones, and then associated with cholesterol are the lipoproteins. Lipids do tons of things in the body. They are a high density form of energy. They have less oxygen on them, so you could say they are more reduced than carbohydrates, and so they give you much more energy per gram. The breakdown of lipids is much slower, though, so they tend to be used during low intensity activity. They're great for energy storage. They're not attracted or bound to any water, so they efficiently store energy as what we call adipose tissue or blubber, and mostly that's just triglyceride form of lipids, and that's how we can store energy as fat. They make up our cell membranes with their phospholipids, which is what controls the flow of substances in and outside of your cells. Some of the sex hormones or some hormones, including the sex hormones, are lipids, including like testosterone and progesterone. They help insulate you and keep you warm with the layer that's under your skin. They help insulate your nerves to help nerve impulses travel more quickly, that myelin sheath around nerve cells. They provide protection for some organs, and they are essential for absorbing fat-soluble vitamins. So they do tons of things. If you can remember 3 or 4 of these, you should be good for the IB exam. So first, we're going to look at the structures of triglycerides and phospholipids. Triglycerides are the main components of what we call fats and oils. Fats is what we're going to talk about when we talk about saturated fats, and oils are unsaturated fats because they tend to be liquids. Structurally, they're formed from glycerol, which more technically could be called propane 1,2,3-triol for these 3 hydroxyl groups, and 3 fatty acid molecules. A fatty acid is simply a carboxylic acid group or a carboxyl group followed by a long hydrocarbon tail. So that's why they're called fatty acids. This part makes them fat soluble, and they are acidic because of their carboxyl group. So when glycerol undergoes 3 condensation reactions at each one of these hydroxyl groups with 3 fatty acids, you formed a triglyceride, and that's shown down below. Here's glycerol. Here are 3 fatty acids. So 3 water molecules can be removed, and you end up forming these 3 ester bonds. So the bond that holds together triglycerides is the ester functional group. So we've seen that in each category of molecules, there's a particular functional group that is sort of the link that holds them together. And so triglycerides are really triesters. They have this ester functional group holding them together. Now, the triglyceride that's shown here has all the same fatty acid, but the 3 fatty acids don't have to be the same. Some can be saturated, some can be unsaturated. It can be a mix. So the triglyceride tends to be categorized by whichever type of fatty acid is most common within it. Something that was skipped over just then is fatty acid structures. We have saturated fatty acids, and when things are saturated, they have the maximum number of hydrogen atoms bonded to them. In other words, it means that all the carbons and hydrogens and all the carbons are bonded to one another with single bonds. So all single bonds for a saturated fatty acid. Unsaturated could be monounsaturated or polyunsaturated, pretty straightforward of the meaning. To be unsaturated means to have 1 carbon-to-carbon double bond or more. And so monounsaturated means 1 carbon-to-carbon double bond, 1 alkenyl group, versus polyunsaturated would mean more than 1 alkenyl group on the structure. So removing 2 hydrogen atoms and replacing it with this double bond. Phospholipids are pretty similar. They're made of glycerol and 2 fatty acids, but instead of that 3rd fatty acid, like in a triglyceride, the first thing that happens is there's a phosphate group, and that condenses with the third OH group in the glycerol, and that's this oxygen right here. That would have been the H off of the glycerol, and it would have been the OH off of the phosphate, but they condense together and form that bond right there with phosphorus. And then there is a nitrogen-containing alcohol. You are usually allowed just to say choline if you don't want to remember a nitrogen-containing alcohol, which is condensed onto the phosphate on the other side. You don't see that it's an alcohol anymore because, again, a condensation reaction has already taken place to bond the choline up to the phosphate. So for a phospholipid, there's actually going to be 4 condensation reactions that take place. One to form this ester bond, one to form this ester bond, one to form the bond with phosphate to the glycerol, and one to form the phosphate to the choline, or the nitrogen-containing alcohol on the other side. The key is that the phosphate is quite polar. It's actually charged, and the choline actually has a positive charge as well with that nitrogen. And so you've got this part up here, which is very hydrophilic. Everything in here is polar or charged, so it's going to have a nice attraction to water. And then you've got these fatty acid tails, which you can see are largely going to be C and H, and therefore nonpolar and fat soluble. And so the representation in a lot of biology textbooks looks like this funny little squiggly double-tailed sperm-looking thing. Anyways, that's what the phospholipids, that's how it get represented in cartoon form. But when they are together, they naturally have their hydrophobic tails will go together away from the more aqueous polar water environment, and the hydrophilic head portions point both to the outside of the cell and also to the inside of the cell where it's largely water. And this space in between is the hydrophobic region where the tails are. So we've talked about just then the condensation that forms triglycerides and phospholipids. Well, hydrolysis is, of course, the reverse reaction where you use a water molecule and you break it apart. This can be aided by during digestion by enzymes, which can be called lipases because they break down lipids. It's also used in soap making, and so sometimes it's called a saponification reaction. Usually soap, well, it can be done in acidic or basic conditions, but usually a strongly alkaline solution is used, such as sodium hydroxide. So what happens if you're using sodium hydroxide and a fat such as stearic acid? Now, this is a saturated fat. It's from the data booklet because I see all CH2 groups here, which means everything is fully saturated there. So if we were to react sodium hydroxide with stearic acid, we would end up with sodium. The H would be lost from the acid and react with the OH in the NaOH, so we'd get water as a byproduct. And we'd end up with this this molecule, or this sort of ionic compound, which would be the sodium plus ion, and stearate, which is would be a negative ion here. And that's shown down below in this vertical diagram. This is the stearate molecule, and this is the sodium ion. And so that's really what soap is. Traditional soap is the salt, or the ionic compound of a fatty acid. What happens when you put this in water is the sodium ion is going to dissociate off of it, and you're going to be left with all these fatty acid ions. And the fatty tail part can interact with things that are oily, things like grease, butter that you get on your hands, and surround those oil particles, while the hydrophilic head, the carboxyl group, will stick out into the water and essentially allow you to wash away oil particles or fatty particles by surrounding them in such a way that you make a particle that has a hydrophilic surface. So that's how the hydrophobic tails will interact with oils and help you clean off your hands. Obviously, typical hydrolysis reactions, I think what this page skips over, usually if it's really a triglyceride, then a triglyceride would require 3 molecules of water for the triglyceride to be split to form 3 fatty acids. So 1 triglyceride and 3 waters will make 1 glycerol and 3 fatty acids. And so I apologize that's not shown here. The condensation was shown on the previous page, and this is essentially would be the reverse reaction, would be to start here, add 3 waters plus a strong acid or base or a lipase, and go back to these things over here as the products. Okay, the last type of lipid to know about is cholesterol and the steroids. So I've shown a picture of cholesterol here from the data booklet. This is the structure. Notice it's almost entirely hydrocarbon with this one OH group. The key structural feature of cholesterol is a steroid, is the steroid backbone, steroidal backbone. And that's this structure of 4 rings right here. So if you're asked to draw the steroid backbone, it is these 3 hexagons and 1 pentagon connected together. The double bond is not really part of the steroid backbone, nor are these methyl groups or other things. It's just the 4 rings. That's what is the steroidal backbone. It's one of the most important steroids in the body. It has all sorts of functions. It's used to make the sex hormones. It's used to synthesize bile acids, which are used in digestion. I realized I spelled this word wrong every time, so let's fix that. Synthesis. It's still spelled wrong. There we go. So synthesis of sex hormones, bile acids, and it can be used to synthesize vitamin D in the presence of UV light. If you look at the structure of vitamin D, it's pretty darn close to cholesterol. There's just a small structural change where this ring is broken, but the other rings and other parts pretty much stay intact. So that's the little conversion there. It also plays a role, cholesterol, in the cell membrane and helping it to be permeable and flexible. The hydroxyl group here can be associated more with the hydrophilic portions of the phospholipids, and the rest of it can point inside along with those hydrophobic tails. I see another typo, man. There we go. While we're on the subject of cholesterol, we'll cover cholesterol and steroids. So cholesterol risks, it's very important, but it's not essential for your diet because your body will produce it on its own. So if you eat too much of it, a very common thing that can happen is that you get this buildup of lipid material, mainly of cholesterol, in the walls and the lining of your arteries. And that restricts blood flow. It's known as atherosclerosis. I'm probably saying that wrong, but that's how it's spelled. And it can lead to high blood pressure and heart disease. You've probably heard of good and bad cholesterol. Those terms actually refer to low-density lipoproteins and high-density lipoproteins. Cholesterol, like the other lipids, is nonpolar, and so to transport it around the body, you need to package it up in something that can move through the largely aqueous environment of the body. And the job falls to the lipoproteins. So they are these sort of lipid/protein structures. There are low density ones, which are larger and are mostly composed of triglyceride and cholesterol. So these are the low density lipoproteins. Having a lot of these in your blood is associated with eating more saturated and trans fats. Both of those lead to more of these in your blood. And it's generally thought to lead to the deposition of more cholesterol in those artery walls. So LDL is the bad kind. High-density lipoproteins are smaller, and they're mostly composed of proteins. They are thought to remove cholesterol from your arteries and bring it to the liver for processing. You get higher levels of HDL lipoproteins or HDL cholesterol when you have higher amounts of unsaturated fatty acids in your diet, especially omega-3 and 6 fatty acids, which are the essential fatty acids. And they seem to help protect against heart attack. Steroids, both natural and synthetic versions of male and female sex hormones, are what we normally think of when we hear that word steroids. Female sex hormones are used as a contraception for the birth control pill. The high levels of female sex hormones prevent ovulation from happening, and as a result, they prevent pregnancy. They also are used as hormone replacement therapy for menopausal women, which can help prevent osteoporosis. When women go through menopause and their estrogen levels drop, that can lead to very rapid deterioration of bone density. And so sometimes women continue to take female sex hormones to help prevent that. The male sex hormones are known as anabolic steroids because we know that word anabolic means to synthesize or to build larger molecules. So anabolic steroids help promote tissue growth, especially muscle tissue. They can be used as part of treatment for cancer, specifically testicular and breast cancer. And they're also known, besides being anabolic, as being androgens. They give male sexual characteristics, so they can be used to aid the onset of puberty or to aid in a sex change regimen. There are hazards associated with steroids use. There's a long list here. I'm going to ask you to look over it. This is straight from an IB mark scheme, all of these reasons. So you wouldn't have to know all of them, but knowing a couple of the general hazards associated with the use of steroids and sex-specific hazards is important. And also some of the issues associated with steroids. So we know that steroids are banned from competitions, and that's because they give unfair or unethical advantage in unfairly promoting tissue growth. But they are important to research because they do have a lot of positive medical applications, and it's important to understand their side effects. And it's important to continue to research them so that we can better detect them when they're banned in competitions. The final things to go over for the structural issues for the SL portion. Saturated fats all have a general formula of CnH2n+1 and then COOH. So they all have that carboxyl acid group, and then their tails are completely saturated, and therefore they have whatever the N is, they have CN2N+1. It's not CN2N+2 like an alkane, because in place of that last hydrogen, there's this carboxyl group. So that's the general formula of all saturated fats. Their relative melting point is high because they're relatively straight. You can see that when they get represented either as perfectly straight lines or as nice straight zigzaggy lines. And so because they are straighter than unsaturated fatty acids, it allows them to pack closely together, which increases London forces and therefore increases melting point. The health risks associated with diets high in saturated fat, we've already talked about them. The buildup of cholesterol deposits in the artery walls, high blood pressure, heart disease, and obesity. Unsaturated fatty acids, as we've already mentioned as well, key structural feature is a alkenyl group or a C to C double bond. They have relatively low melting points because that's the C to C double bond is generally the cis form, which the HO group will know what that talks about, but essentially it puts a kink in the tail. Sometimes that language can be used, kink in the fatty acid tail, and this prevents close packing and lowers the London forces in it. And so most unsaturated fats we call oils because they are liquids at room temperature from that lower melting point. The health benefits associated with them is a reduced risk of cardiovascular disease and better neurological development. The last topic really for lipids, there'll be one calculation to do in a subsequent video. The last topic is rancidity in fats. So when fats go bad and they start to smell or taste nasty or look gross, there's two different ways this happens. Hydrolytic rancidity, think of it as, well, hydrolytic means hydrolysis. So this is going to be a similar type of reaction to the other hydrolysis reactions we've learned for fats, which is that it goes after their ester bonds in the triglycerides. So hydrolysis, this is just the normal hydrolysis. The ester bonds are breaking apart. The mechanism uses water, and that it hydrolyzes the ester bonds, releasing the glycerol and the fatty acids. Fatty acids, some of them smell horrible. Butanoic acid smells like vomit. Not sure what octanoic acid smells like, but it probably smells pretty terrible. So when you cleave the glycerol off and you're left with fatty acids, if they're in this sort of medium range, they smell really, really terrible. This is promoted by high temperatures and the presence of certain enzymes like lipases that can be around if there's more bacteria around. The best way to prevent it is to refrigerate your things that contain fats. But this kind affects unsaturated and saturated equally because they all have those ester bonds. Oxidative rancidity, on the other hand, primarily affects unsaturated fats. And for this reason, saturated fats are more stable overall than unsaturated because they are not affected by this kind of rancidity. The C to C double bond is more reactive than the single bonds of the saturated fatty acids. And so the oxygen is reacting with that C to C double bond. The oxygen tends to come from the air, and it breaks down the fatty acids into aldehydes and ketones that are volatile and smelly. This is sometimes called autooxidation, and it occurs more readily in the presence of light, metal ions, or certain enzymes, and it can be reduced by packaging that can block light or that prevents things from coming directly in contact with certain metals. But also you can add additives to the fat, to the oils that are called antioxidants and therefore prevent the reaction with oxygen.